Hello, Dr. Foley again. Let's get into Chapter 2 material. We're going to discuss atomic theory, learn about the structure of atoms and ions. We'll discuss the difference between atoms, isotopes, and ions, learn how to write and draw some chemical formulas for atoms and compounds, and then introduce the mole concept and Avogadro's number, which we'll talk about in a later chapter, but I want to just introduce it to you early in the course. I'm following the book pretty closely for now, as I said. So a lot of this, if you read the chapter, you're going to read a lot of what I'm actually following along here. These are PowerPoints directly from the text. So how do atoms fit into everything, especially molecules and compounds? So as you know, molecules consist of atoms that are chemically bonded. Before we can understand how chemical bonding works, we need to learn a little bit more about what atoms are that make up these millions of different compounds. What you see in this picture is somebody exhaling into a machine called a mass spectrometer. It's actually a gas chromatograph that separates a mixture, and then the different molecules go into a machine that actually tells you the mass of the molecules. And none of that technology would be possible if we didn't understand what atoms were. So let's just kind of have a history lesson here and follow along in this outline with me. So we want to review Dalton's atomic theory, which came about a couple hundred years ago, and use his postulates of his theory to explain the formulas that we come up with, which like H2O or CO2. Those are formulas that obey these laws of definite and multiple proportions, they're just explaining how atoms bond and the ratios that they bond in. It's all based on whole number ratios. The concept of atoms was first proposed by Greek philosophers, about 2,500 years ago. Democritus was the one that really was ahead of his time. Philosophers like him and others proposed the existence of atoms long before they had the technology. And the word atom comes from the Greek word that they used they knew that they proposed that matter was indivisible. And that's what the word atomos means, or the word atom, it comes from the Greek word for indivisible. And back then, and until about the 20th century, we thought that atoms were indivisible, but we now know that they're made of more fundamental particles. Later, Aristotle and others believed that matter consisted of various combinations of 4 elements: earth, fire, air, and water. And we now know that that was completely wrong. But Democritus's idea of indivisible atoms was ignored until almost 2,300 years later. So if we hadn't ignored the theories that he proposed all those centuries ago, we probably would be much farther ahead in our technology. But we've made a lot of progress since 1807, when a guy named John Dalton in England came along and proposed his atomic theory. He apparently did a lot of work with, he did a lot of experiments in which he took elements and reacted them with oxygen, and he did a lot of careful weighing of different compounds, and he was able to come up with a theory of how atoms worked and how things combined together. So he came up with these postulates that still are true today. Matter is composed of exceedingly small particles, and we call them atoms. And an atom is the smallest unit of an element that can participate in a chemical change. But we now know that atoms are made of protons, neutrons, and electrons. An element consists of only one type of atom, which has a mass that's characteristic of that element and is the same for all atoms of that element. What does that mean? It means that if you look at carbon, they all have the same, they're all made of the identical atoms. There aren't different types of carbon in the sense that they have different numbers of particles. They might vary slightly in how many neutrons they have, but the number of electrons and protons that atoms of an element have are always identical. Atoms of one element differ in the properties from atoms of other elements. like the boiling point, the melting point, the electronegativity, things like that that describe how different atoms behave when they bond to different elements. Now, a compound consists of atoms of two or more elements combined in a small whole number ratio. Like I said, H2O is a compound. It's made of hydrogen and oxygen, different elements. In a given compound, the number of atoms of each of its elements are always present in the same ratio. So no matter where you look on Earth, it's always going to be H2O. You'll never see a molecule of water that's H3O or HO. Atoms are neither created nor destroyed during a chemical change, but instead rearranged to yield a different type of matter. That's a fundamental law of the universe called the law of conservation of mass. So ever since the beginning of the universe, there's all the mass that existed then is identical to the mass that exists now. All that's changed is how the mass has been redistributed and combined into different types of atoms into different molecules. So if you magnify thousands or millions of times under an electron microscope, you would actually see individual spheres of atoms. If you look on the internet, you can actually see pictures of atoms. They can see these with an instrument, and we have one at the University of at the Oshkosh campus. So they're routinely used in research. It's called an electron microscope. It actually uses an electron beam to bounce off the material, like in this case the surface of a penny, and you can actually see the tiny little atoms in arrangements that look somewhat similar to this. And that's a pre-1982 copper penny. Contains approximately 3 × 10⁻²2 copper atoms. And this is just a little piece of how what it would look like on the surface. Copper oxide is another type of compound. So when copper is oxidized, it forms copper oxide, a black compound. But notice that they always combine in a 1-to-1 ratio. That's part of Dalton's theory. So whenever atoms combine, probably is pretty obvious to you that they always combine in a whole number. There's no such thing as a half of an atom. It's always one whole atom combining with another, or it could be a couple of them, but they always combine in whole number ratios. So Dalton's theory explains the law of conservation of matter. It provides a microscopic explanation of the macroscopic properties that we learn about, the density of a material or its boiling point or its melting point. Those are properties we can measure in a lab, but all those things are explained, and how chemical compounds are formed are all explained by Dalton's theory of atoms combining in these whole number ratios. If atoms are neither created nor destroyed during a chemical change, then the total mass of matter present when matter changes from one type to another will remain constant. That's the law of conservation of matter, or the law of conservation of mass. So here's some visual examples in your text. We can represent a chemical reaction, a simple one like this. An element or a compound represented in green combines with a compound in blue, and it forms, they combine. One of these combines with one of those. That would violate the law of conservation of matter. You have 4 atoms on the left, only 2 on the right. All chemical reactions always obey this. If you combine 6 atoms on the left, you get 6 atoms on the right. But this is all a chemical reaction is. It's the same number of green atoms on the left as on the right, 2 blue on the left, 2 blue on the right. And that's it. And all we're going to do in this class is learn what these green and blue spheres are. You're going to look at the periodic table, and you're going to use symbols to represent different compounds. The other important consequence of Dalton's theory is what's called the law of definite proportions, which states that the numbers of atoms of the elements in a given compound always exist in the same ratio. That's what I was saying earlier. Water is always H2O. Carbon dioxide is always CO2. No matter where you find it, whether you find it here or on Mars, it's always going to be the same ratio. The law of definite proportions, or the law of constant composition, it's called. All samples of a pure compound contain the same elements. And this was illustrated by experiments done by a French chemist in about the same time as Dalton. His name was Joseph Proust. He did a lot of experiments like Dalton did. And so for instance, they took various amounts of elements. I'm not sure how they did it back in their day, because all they had was glassware. They didn't have any machines like these instruments that we have today. They had to do a lot of careful weighing and measuring and observation to come up with these theories. But it's for instance, if you have a compound called isooctane, no matter how much hydrogen you start with, it's always going to combine with the same amount of carbon ratio-wise. So if you 2.78 grams of hydrogen combines with this amount, if you take the ratio between 14.82 and 2.78, you get a 5.33. That should really be 5.33 to 1 ratio. Maybe I should change the color of my pen here. 3.63 grams would combine with a little bit more carbon, but that's still a 5.33 to 1 ratio. And that probably doesn't mean much to you right now, but when you see the formula of isooctane, it'll make more sense to you. I'm just giving you the basics of this theory and how all of this stuff led up to our present understanding of how molecules and the formulas that they have are where that all came from. The law of multiple proportions states that when two elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in a ratio of small whole numbers. Okay, that's a confusing statement. What does it really mean? Well, your book gives you this example. Compound that contains has 0.558 grams of chlorine to 1 gram of copper. They found that that's true. But then if they doubled, if you double 0.558, there's another compound that's brown instead of green that contains double the amount of chlorine for every gram of copper. So you can see that's the law of multiple proportions. When two elements react to form more than one compound, chlorine and copper, a fixed mass of one element, in this case copper, will react with masses of the other element in ratio of small whole numbers. So that's a 2 to 1 ratio. That's what that means. Twice as much chlorine is in one compound as the other. And what that really means then is that the green compound has the formula CuCl, and the brown compound has the formula CuCl2. Why one is green and one is brown we'll worry about later, but the colors of compounds is a function of the structure and the electrons. What you're going to learn pretty quickly is that electrons are the key to the reactivity of all atoms and compounds. And it's hard to see in this picture, but this is kind of what an ionic compound like copper chloride looks like. One is, this picture is compared to the copper chlorine compound in this part, where copper is represented by brown spheres and chlorine by green. The copper chlorine compound of B has twice as many chlorine atoms per copper. So this would represent the structure of CuCl, and this would represent the structure of CuCl2. And if you look carefully in the online textbook, you will see that that's true. These green spheres are surrounded by exactly as many brown spheres as the brown spheres are surrounded by green spheres. So ionic compounds like this, when I say ionic compounds, which we'll talk about shortly, are compounds that contain a metal. The other type of compound is called a covalent compound or a molecular compound like water. And there's a big difference between the two types of compounds, which we'll discuss a lot. So again, this is the spheres just represent atoms, and within each of these spheres, we're just using different colors to clarify it, but all these spheres, whether they're green or brown, are made of three fundamental particles: protons, neutrons, and electrons. So the next video will talk about how these three particles were discovered. All right, so this part will be a bit of a history lesson in the evolution of atomic theory. This all occurred about about 120 years ago, around the turn of the 19th to 20th century. There were some scientists in England. One of them was J.J. Thomson. They did some very important experiments, and their discoveries are still true today. So they helped us understand what's within these little spheres, which everybody's heard of protons, neutrons, and electrons, but I want to review with you how they all fit together in atoms. So we're going to talk about what atoms what are atoms composed of, and is there something smaller than an atom? Of course there is. The electron was discovered by Thomson, and he experimented with cathode ray tubes. You probably heard of cathode ray tubes. They were early types of television, and even computer monitors. CRT tubes were based on this principle. A cathode ray tube is really just a sealed glass tube. This is a schematic diagram of one. And it has almost all of the air removed, and it contains a couple metal electrodes far apart. And what happens is you run an electric current through this tube, and a particle or a beam of particles is generated. The sealed glass tube, which is almost a pure vacuum, so there's no molecules or atoms to get in the way, it contains two metal electrodes, and when you apply a high voltage across the electrodes, a visible beam called a cathode ray appeared between them. Now they called it a cathode ray because it started from the cathode, which is a negatively charged, it has a negative polarity in this particular instrument. So that's where the name comes from. What was interesting was, regardless of the metals used, so they put a little piece of metal right about here, gave it a negative polarity with some electronic circuit, and they saw no matter what they observed, whatever element they used, the particles always had the same characteristics. So regardless, the beam was always deflected toward the positive charge. So as it passed through, it was accelerated toward an anode. So the anode was positively charged. So if these particles were originated from here and they were accelerated to a positive charge, they're probably negatively charged particles. And as they passed through another electric field that was 90 degrees to that, they noticed they were deflected upward. So this part of the tube is just to get the particles to accelerate. They're repelled by this part and attracted to this. And as they pass through this part here, they noticed they were deflected up. So they must be attracted to the positive charge, and that's why they proposed they had a negative charge. Very obvious observation we would all make. Thomson was able to calculate with some careful measurements the charge to mass ratio of the cathode ray particles. At that time, he didn't know they were called electrons. He just called them cathode ray particles. But he knew that they were much lighter than atoms, and he noticed that they must have been negatively charged because of the way they behaved as they passed through this part of the cathode ray tube. These particles were indistinguishable regardless of the source material. So these particles were emanated from all metals. So he proposed that they must exist in all atoms. This cathode ray particle is now called an electron. I think it came from electric ion. Some other scientists proposed that they behave like electric ions, so they combine that into one word, electron. So we now know it's a negatively charged subatomic particle, which means it exists within an atom. It has a mass more than 1,000 times less than that of the atom. So he was able to figure that out. It was that light because I'm not sure exactly how he measured the charge to mass ratio, but he came up with the fundamental charge of an electron, which was a huge achievement for his time. And that's the basics of, that's really the main experiment where we discovered what an electron was. Now, there was another important experiment done by a guy named Robert Millikan in 1909, and he did what's called the famous oil drop experiment. He created microscopic oil droplets, which he gave an electric charge to. So if you study this diagram in your book a little bit, you'll see that he had an atomizer of oil. I'm not sure the oil he used, but he sprayed it into a chamber. And the chamber was, I believe it was evacuated. It was a vacuum. This is just a cutaway diagram, a cross section of the instrument. And he had a telescope where he could actually see the drops, and he was able to control the speed at which they fell. He can actually suspend them in the air by having oppositely charged plates. So he was experimenting with electrons and figuring out their charge. He used X-rays to zap the electrons, or the oil droplets, sorry, to strip electrons from them. So he had variously different, he had different charges on different drops, and he had no control over that. He just observed that some drops had a higher charge than others. So by varying the electric field between these two plates, he could kind of notice that some drops had a charge of one type and some had a charge of another type. But what he always noticed was they always had they had a fundamental charge of 1.6 times 10 to the minus 19th. That sounds like a random number, which it is. It's like Avogadro's number. It just is what it is based on our instruments. There's no reason why it's 1.6 times 10 to the minus 9th. It just is. But that's what you notice. This is some of sample data that he noticed that some of the drops were the fundamental electric charge, and they were always a multiple of that number. So it was either double it, 3.2 to the negative 19th, or maybe 3 times 4.8 times 10 to the negative 19th. It's hard to read that, but this is in your book. Or maybe it was 4 times. He noticed that they were always they were a multiple of that fundamental charge. So then he concluded that this 1.6 to the negative 19th was the charge of a single electron. So since Thomson had already showed that the charge to mass ratio was 1.759 times 10 to the 11th coulomb per kilogram. So that's a huge number, 10 to the 11th. But that makes sense because if you have a kilogram of electrons, that's a huge number of electrons. So it's going to have a rather large charge. And each electron only has that much of a charge. So this is what they did. They combined their data, and if you take the ratio of the charge of an electron divided by its charge to mass ratio, you actually get the mass of an electron in kilograms. It's very, very tiny, as you can imagine. It's 9.107 times 10 to the minus 31 kilograms. So that's important to us in chemistry because we can really ignore the mass of the electrons when we calculate the masses of atoms. If we include it, which we should, we notice that it doesn't occur until like the 5th or 6th decimal place. So we generally ignore the mass of electrons when we're calculating the masses of atoms. Thomson suggested that atoms resembled a plum pudding model. So based on all this data, Thomson came up with this plum pudding model where he pictured atoms as having positive charges and negative charges kind of equally distributed in 3 dimensions. He was from England, so I guess plum pudding was a popular food there. But that we found to be wrong. There was another scientist who proposed that atoms resembled the planet Saturn with a ring of electrons surrounding a positive planet. So which one of these was correct? It actually turns out that this is more plausible. This agrees more with what we've discovered since this time, that atoms really look quite a bit like this model. We call it the solar system model, or the planetary model of the atom. And then came along a guy named Ernest Rutherford about the same time, who did probably the most important experiment of all. And he performed what's called the gold foil scattering experiment. And what he did was along with some of his grad students, took a beam of alpha particles. Now, an alpha particle is just a positively charged particle, and it's one of the 3. I believe there's 3 fundamental radioactive particles. There's alpha particles. This is the Greek letter alpha. It looks like the symbol for a fish, kind of. It's the Greek letter A. There's alpha, beta, gamma, delta, etc. But anyway, this alpha particles are similar to helium atoms, but they have their electrons stripped away. So an alpha particle has the same characteristics as if you took 2 protons and 2 neutrons and put them together as one unit. But anyway, some matter, when it decays, in this case radium, which is one of the chemical elements, but it's radioactive, hence the name radium. It was in a lead blocks because it's dangerous to work with. So they only allowed the beam of particles to exit it at one side of the block. So they had a very concentrated beam of electrons. Now I have another diagram I'll show you, because I realize this is kind of small on the page, but this again is in your textbook, so you can kind of follow along if you'd like. Again, he knew that the alpha particles were positively charged, and the scattering of these particles was examined. So he kind of had a screen around the gold foil. I don't know how far apart these were. I'm imagining maybe 3 to 6 feet apart in a lab somewhere in England. And he had some screen, kind of like a film in a camera, that would light up. It would make a little image when an when an alpha particle would hit it. So what he noticed was that a very small number of the alpha particles were significantly deflected. That was his most stunning result. As he expected most of the alpha particles to just pass right through the gold foil. This is like a piece of aluminum foil, but it's made out of gold. It's very, very thin. So he kind of had the idea that atoms were made of. He knew that they had electrons and protons, but he didn't know where they were. And he knew neutrons existed at the time, I believe, as well. But he didn't really know, and others didn't know really what the atom looked like. Did it look like this? Or did it look like that? Or did it look like something they hadn't thought of? But these results kind of provided a lot of support for what came next. But most of the alpha particles went straight through. A few were deflected at small angles, and some of them came right back. And so his results were this. The volume occupied by an atom must consist of a large amount of empty space, because most of these alpha particles just passed right through. A small, relatively heavy, positively charged body, which is called the nucleus, must be at the center of each atom. And he proposed that because of his results. A few of the particles actually came back at him. And that was extremely surprising to him. He proposed that the nucleus contains most of the atom's mass, and negatively charged electrons. Let's see, I forgot how to spell. Negatively charged electrons surround the nucleus. The proton, which is a positively charged particle, positively charged subatomic particle, is located in the nucleus. Those were what he proposed. All his results were based on these simple observations. So there's a closer view in your book that shows what was going on. The alpha particles are deflected only when they collide with or pass close to the much heavier positively charged gold nucleus. Because the nucleus is very small compared to the size of an atom, very few alpha particles are deflected. Most of these particles pass through the relatively large region occupied by the electrons, which are too light to deflect rapidly moving particles. So let me just clarify that with this larger diagram here. I think that's in view. So again, I'll restate what he discovered with this and show you why he came up with his results, which I just stated to you. About the nucleus containing most of the must be at the center of the atom, and then the nucleus contains most of the electron's mass, and the atom's mass, and the negatively charged electrons surround the nucleus. So he knew again that these alpha particles coming out of this the element radium were positively charged. So most of the particles pass right through the foil. Most are undeflected. He expected that, because atoms are mostly empty space. So the beam passes through the gold foil as if it doesn't really see the atoms. A few of these particles are scattered at various angles, probably because they came kind of close. Some of the alpha particles, as they came close to this, you'll have to look more closely in your book, but as a particle comes close to the nucleus, which is at the center of these gold spheres, The nucleus, we now know is where the protons are, which are positive charges. So if the alpha particles coming in are positively charged and they pass close to a positive nucleus, they're going to be repelled. Positive charges repel each other, and negative charges repel each other. So they repel each other, and that's why it was deflected at a slight angle. If the beam passes through the part of the atom where there's no electron or there's no positive charge, kind of on the outside of the atom, which is shown here as the boundary between a couple layers of gold atoms, the alpha rays, which are positive, again, aren't deflected at all. And that was a result he expected. But these results where the alpha particles actually bounced back at the screen. So every time an alpha particle was deflected, it made a little image on this screen. It was fluorescent. It's like it was showing a little beam of light. This was extremely surprising. The only way he could rationalize this was that every once in a while an alpha particle would hit a direct hit on a gold atom's nucleus. And since these were positively charged and it hit head on a positive nucleus with a lot of mass, it was like two billiard balls on a pool table colliding. They bounce off each other. And so these results were very startling. I think he said something like, it's almost as if he fired a missile at a piece of tissue paper and the missile bounced back. That's how surprising these results were. So the only way he could rationalize that was to say that atoms must be something like this, a spherical region of space. This is three-dimensional, but this is flat. We got to think in 3 dimensions. The positive charge is here and the negative electrons are here. So he actually helped people like Niels Bohr come up with our present understanding of the atom. All the mass is in the nucleus where the positive charge is, and the electrons orbit around it. All right, let's move on to the next important discovery, which was the third fundamental particle, which is a neutron. I don't know a lot about how it was discovered, and it's not terribly important to us. But some of the other important discoveries, or one of the other important discoveries besides discovering the neutron, was the presence of isotopes, which are atoms of the same element that differ in mass. So we're going to discuss a little bit about that. Isotopes are extremely important in medicine and chemical research and radiocarbon dating, but they're essentially different flavors of an atom. A guy by the name of Frederick Soddy in England discovered the fact that isotopes existed. But another guy named James Chadwick discovered through some experiments I'm not familiar with that there were uncharged particles as well. So they had already discovered electrons, which are negative, and protons, which are positive. And there's a third particle called a neutron. And since the word neutral means, in one context, means no charge, they gave this particle the name neutron. They're subatomic particles, and they found that they had a mass about the same as that of a proton. And that's an interesting result that will help us understand the masses of atoms in a little bit. Neutrons are also found in the nucleus. I'm not sure how they figured that out, but they were through various experiments they found, and they were able to, with our modern instruments of today, we were able to actually figure out the masses of these particles. But they turn out to be very similar. I don't know how well my pen's going to write on this yellow highlighted ink here, but the mass of a neutron is 1.67493. Don't worry, you won't have to memorize this number. I just want you to appreciate its size. That blue pen is not very good. The point is worn off. That's 1.67493 times 10 to the minus 24th grams. And they discovered that a proton had a mass slightly less, 1.67262 times 10 to the minus 24th grams. And these masses make sense. We're talking about subatomic particles. They should have a very, very tiny mass, but they're almost identical. That was an interesting result. There's some fundamental particles that have the same mass, but one has a positive charge, one doesn't. but now with our present understanding of matter, it all fits together rather nicely. And if you compare the mass of an electron to that, the mass of an electron is tiny, tiny. The mass of an electron, I had on a previous slide, but it's 9.10933 times 10 to the minus 28. I think I had it in kilograms in the other video. Let me just check back at what I said it was. It was 9.107 times 10 to the minus 31st kilograms. Well, the other source, but depending on the source you find data, you're going to have slightly different numbers. But this is pretty darn close to that. But it's in grams, so it's 10 to the minus 28. So it's what? It's about 1/2000th the mass of a proton or a neutron. So we say the masses of the electrons are essentially insignificant when we calculate the mass of an atom, and followed by the masses of compounds. All right, so that's just a quick review of how we discovered the three fundamental particles that all matter is made of. Let's talk about the symbolic representation of atoms now. So atomic structure and symbolism. We want to write and interpret some symbols that depict the atomic number. So there's some new vocabulary for you. Atomic number I want you to learn, mass number, and electric charges. I want you to learn or understand what an atomic mass unit is, and what the average atomic mass of an element is, and how to calculate it, and understand how isotopes fit into all that. So here's what we know about atoms at this point. The nucleus contains the majority of an atom's mass, so we can ignore the mass of the electrons. Protons and neutrons are much heavier than electrons, and I think that's probably not visible on the screen here, but I'm going to represent sometimes the proton with a lowercase p with a superscript positive charge, and neutrons will often be drawn in my notes as a lowercase n with a superscript 0 to represent that it has no electric charge. Electrons occupy almost all of an atom's volume. They orbit around the nucleus. The diameter of an atom is about what we measured on average. The diameter of an atom is about 10 to the negative 10th meters. That's 1/10 of a nanometer. That's 1/10 of a billionth of a meter. That's actually a special unit called an angstrom. It's not a metric unit, so we generally don't use it, but it has the symbol A, capital A with a circle over the top. That's 10 to the negative 10th meters. And they discovered, or we proposed or measured in some way, the diameter of a nucleus is about 100,000 times smaller, at about 10 to the negative 15th meters. So here's a picture of what a basic picture of what an atom looks like. You have a very, very tiny nucleus on the order of 10 to the negative 15th meters, and an average atom, probably hydrogen, is about 100,000 times larger than that. And there's all sorts of analogies that we use to explain to students, like this. If an atom could be expanded to the size of a football stadium, the nucleus would be the size of a single blueberry in the center of the stadium. Another analogy is for a hydrogen atom. If the nucleus is the size of a golf ball, the electron, where do you think the electron would be? Well, here's the answer. I use in all my classes to kind of give an analogy of how much empty space is in even the simplest element, hydrogen. So this is called the scale model. You might have made a scale model of the solar system when you were in grade school to kind of show you how far apart the planets really are. The nucleus of the atom has a diameter of about 10 to the minus 15th, whereas the atomic diameter is 10 to the negative 11th. Well, I said it was 10 to the negative 10th. So depending on this is what you'll also discover when you take science classes. Depending on the source of your information, maybe Wikipedia or some other source, you can get conflicting information. My point is to always be skeptical about what you read, double check things, and also understand that there are slight discrepancies in the information that we know. This probably, I got this many years ago, so maybe this is more current information where they've discovered that there's there's about 100,000 times difference in the size, diameter difference between a nucleus and the atom itself. But that's not really the point. The point is that atoms are mostly empty space. The great amount of empty space is illustrated by this analogy. Imagine the nucleus to be the size of a golf ball. Then on this scale, the first electron shell would be about 1 kilometer from the golf ball. The second shell about 4 kilometers, the third 9, and so on. If you find that hard to visualize, try this. The period at the end of this sentence, depending on your monitor and the font you're using, is probably about 0.5 millimeter in diameter. That looks about right. If that period represents a nucleus, then the electrons in the first shell are orbiting at about 50 meters around you. In fact, the actual diameter of an atom is very small, and it would require about 200 million of them side by side to form a line a centimeter long. Okay, so I'm telling you things you already know. Atoms are incredibly tiny, but they are really mostly empty space. So another way to look at it is if the, again, as I said, if the nucleus were raised to the size of a golf ball, the first electron would be about 1,000 meters away. And again, that is a direct result of Rutherford's famous experiment, this one here, that most of the particles passed right through the foil. And since atom on this, we understand, is mostly empty space, the center of the atom is where all the mass is. So most of the beams of the alpha particles are going to pass right through the atom because it's mostly empty space, like a blueberry in the center of a stadium. The blueberry is the nucleus. So every once in a while, an alpha particle will hit that blueberry in the center of the stadium, but it's very, very, very rare. So that gave us a understanding, or helped us propose this picture of the atoms that is still pretty much true today. So let's continue. So what do we know about atoms? Atoms and subatomic particles are very small. For example, a carbon atom weighs less than 2 times 10 to the minus 23 grams. Electrons have a charge less than 2 times 10 to the minus 19th grams. So we need to have a fundamental unit that is on that scale. So they invented this thing called the atomic mass unit. A relative mass scale was created to express very small masses as small integral masses close to 1. So they just shrunk everything down. Instead of calling it something 10 to the minus 23, they just said, we'll call that 1. And they had to base it on some element, which we'll talk about shortly. You always have to pick a reference, just like we talked about reference standards for all the different units. The atomic mass unit, which is often called an AMU, is very, very small. It's 1.6605 times 10 to the minus 24th grams. And if you look back at the mass of a proton or neutron, it's very similar to the mass of a neutron or proton. So in a sense, you can think of an atomic mass unit as a proton, about the same size, or a neutron. And so on this scale, or on this system that we've invented, it's totally made up. The mass of a carbon-12 atom is exactly 12 AMU. So they chose carbon. I'm not sure why, probably because it's a very stable element and it's very abundant. They chose one very specific isotope of carbon. So 1 AMU is the mass of one, what I'll call a carbon-12 or C-12 atom. So we're learning some new notation. Chemistry is a very symbolic science, like physics or biology. We represent things with symbols, and that can make it difficult to learn. It's like a language, as I've said many times before. We know the fundamental unit of charge is again 10 to the negative 19th. But how did they discover this? They used that instrument that I mentioned about. They used a mass spectrometer to figure this stuff out. A mass spectrometer is it's a very sophisticated instrument that allows us to actually count individual atoms coming through the instrument, and we know the masses of these atoms coming through. we use electric fields and magnetic fields to deflect and focus particles inside these instruments, and we're able to essentially count atoms, and we're really counting ions, but an ion is, which we'll talk about soon, an ion has essentially the same mass as its parent atom. So on this scale of our atomic mass unit, which is defined relative to carbon-12, the proton has a mass of 1.0073 atomic mass units, and we say it has an electric charge of +1. Again, these are totally made up. These are relative scales. If you want me to clarify what a relative scale is, you can either look it up on the internet or ask me to clarify it in class. But they're totally made up, just to make the numbers nice for us. The electron on this scale, again, the mass of an electron is about 1/2000th of the mass of a proton or neutron. On this scale, it would be about 0.00055 atomic mass units. So almost essentially insignificant, but most important, it carries an equal and opposite charge to a proton. So just to kind of summarize again, most of the mass of an atom, 99.999% of it is due to protons and neutrons. Protons carry an equal and opposite charge to an electron. But what is really crazy is that most of the chemistry that we observe of elements and compounds is due to the electrons, which have essentially no mass at all. So now one interesting thing, I want you to, your book comments on this. So if you just think, what we'll talk about in a little bit, but a carbon-12 atom is made of 6 protons. So if you take, I'll do this in a different colored ink to make it stand out. If you take 6 protons and multiply it by the mass of a proton in atomic mass units, which is 1.0073, and add that, and that turns out to be 6.0438. These are units of atomic mass units. I'll leave them off there. And then you add to that the mass of 6 neutrons, which is 6 times this number, 1.0087 atomic mass units, and that turns out to be 6.0522. And then you add to it 6 times the mass of an electron on this scale, which is 0.00055. That turns out to be 0.0033. So the mass of an electron doesn't occur till the 3rd decimal place. If you add these up, you end up with 12.0993 atomic mass units. So what, you might think? Well, it's supposed to, we would think it would add up to exactly 12, because we've defined this atomic mass unit based on counting isotopes, only one type of atom coming through this instrument, carbon-12 atoms, which are made of 6 protons, 6 neutrons, and 6 electrons. So why does it add up to more mass than what we've measured it to be? Because when you combine particles together, some of the energy is lost, some of the mass is lost to energy, and that's Einstein's famous equation, E equals mc squared, which we've all heard of. That equation is essentially relating the mass of a nucleus to the energy that it contains. Nuclei contain tremendous amounts of energy. If you convert that difference, that 0.0993 atomic mass units that's lost when you combine these particles, it's called the mass defect. When you convert that mass, which appears to be tiny, into energy, you get a huge amount of energy, and that's essentially the principle that explains how atomic bombs and hydrogen bombs work and why they're so destructive. But back to chemistry, that's more physics. So let's summarize all of this information into symbols. So we'll say the number of protons in the nucleus is what we're going to call the atomic number, and that has the element, or that has the symbol capital Z. I'll write it like that. This is the defining trait of an element. The number of protons explains or identifies something as gold or carbon or iron or whatever. That's pretty interesting. For example, any atom that contains 6 protons is carbon and has the atomic number 6, regardless of how many neutrons or electrons it might have. What we'll talk about shortly is that different atoms of an element can have different numbers of neutrons. A neutral atom must contain the same number of positive and negative charges, so the number of protons equals the number of electrons. That's a very important observation to make. Therefore, the atomic number also indicates the number of electrons, as I just said. The total number of protons, just write P plus, and neutrons, N superscript 0, in an atom is called the mass number, which we usually give the symbol capital A. So this is the atomic number, that's the mass number. The number of protons, that's the number of protons plus neutrons. And the number of neutrons is therefore the difference between the mass number and the atomic number, A minus Z. So that's summarized here. Atomic number is Z, mass number is A minus Z is the number of neutrons. So we usually combine it in a symbol. So let's just, some generic element from the periodic table, just call it element X. We'll use notation like this. The atomic number goes in as a subscript, we'll call it Z. The mass number goes as a superscript up there on the, and it's always written on the left. And for example, you'll see in your textbook and other sources things like 12 capital C subscript 6. That's the isotope of carbon with a mass of 12. There's an isotope of hydrogen, has 1 proton, symbol capital H, but a mass number of 3. That means it has 2 neutrons. An element like cobalt, which is a transition metal, it's identified as cobalt because it contains 27 protons, which we write as the subscript, and it has a number of neutrons that add up to give it a mass number of 59. So far so good, I hope. Let's talk about now, instead of atoms, ions, which are electrically charged particles. You can represent ions with the same sort of notation, but you just have to add an electric charge over here on the right, upper right. So sometimes the number of protons and electrons is not equal. That's what's called an ion is formed. The charge on an ion, now again I have this yellow ink that I use, but the number of protons minus the number of electrons will always tell you the charge on an atom. Atoms and molecules acquire this charge by losing or gaining electrons. Why do they do this? They do this to become more stable in a bond. Everything in nature tends to go from a state of high energy to a state of low energy, relatively speaking. So things become generally become more stable, or I should say atoms become more stable when they make a chemical bond. And they become more stable by either gaining electrons or losing electrons. So it depends where they are located in the periodic table. An atom that gains 1 or more electrons will exhibit a negative charge, because if it gains 1 or more electrons, there'll be more negative charge than there will be positive charge. For example, and we call that an anion, so make sure you know that that's a new term for you as well. A neutral oxygen atom, which has an atomic number of 8, and it might help to have a periodic table in front of you to see these things, but you'll notice that oxygen has an 8 in the box where the capital O is. That means it has 8 electrons and 8 protons. If it gains 2 electrons, it becomes an anion, a negative charge with a 2 minus charge. That's the convention we usually follow. We write the negative or the positive after it. So some other examples of anions are things like sulfur would have a -2 charge. Even though I say -2, I write it as 2 negative, and there's a good reason we'll come to at a later time. But try to get in the habit of writing the size of the charge first, followed by the positive or negative. Fluorine has a -1 charge. You can either write it as 1 negative like that, or just F minus like that. I'll usually just do that. When there's no number, it's understood to be 1. So chlorine, which is right below it in the periodic table, has the same electric charge when it forms an anion. And nitrogen, which is a few columns over in the periodic table, you'll start to see patterns now, generally acquires a -3 charge. The other type of ion then would be a positive charge. An atom must lose 1 or more electrons to acquire a positive charge. And we call those things cations, C-A-T-I-O-N. For example, a neutral sodium has an atomic number of 11 protons in the nucleus. Therefore, it has 11 electrons orbiting around it. If this atom loses 1 electron, it will become positively charged because the number of protons, again, the charge on an atom is always the number of protons, the atomic number, subtract from that the number of electrons, in this case -10. So it's left with a +1 charge. And so we would write that as Na superscript plus. But there's many types of cations. For every element not every metal in the table, which are all those elements on the left of that staircase you might see in your periodic table, will always form a positive charge. Magnesium, potassium, and we'll cover in a little bit how we name these things. How do we distinguish these electrically charged particles from a neutral atom? Figure 212, which I don't have in this handout, shows what happens. Oh, that's just talking about if you don't have enough iodine in your diet, which you would consume generally as when you see something like at the store when you go buy salt, you might see iodized salt. Morton's salt is iodized. That's because it contains extra iodine atoms and helps keep the thyroid gland in your body healthy. And so we can combine all this information into chemical symbols for the elements. A chemical symbol, it's just an abbreviation that we use to indicate an element or an atom of an element. So we've already talked about this in chapter 1. The element symbol for mercury is Hg. I wanted you to memorize the first 36. Okay, I've mentioned it again here. Carbon is C, potassium is K, bromine is Br, iron is Fe. Many symbols, as you know, come from Latin or Greek. Some symbols are derived from the common name, others are abbreviations of the name from some other language. Most symbols have 1 or 2 letters, but 3-letter symbols they use for the elements they've discovered more recently. You might have heard of the CERN particle accelerator. I believe it's in Switzerland, but they're doing experiments with fundamental particles, and they've discovered and synthesized other elements, and those would be found at the bottom of the periodic table. But they haven't come up with names of many of these, so they just use 3-letter symbols that are based on naming the number, their atomic number, I believe. But what you should know is that symbols are always capitalized, but only the first letter. So again, to learn more about any element, I really encourage you, just for entertainment purposes, go to periodicvideos.com, and it's really a great resource for learning about all these different elements. The professor looks like Albert Einstein. So I hope you've already gone to check that out, but look at elements like mercury and potassium and fluorine. Those videos, those are the ones I can think of that are pretty entertaining.